Okay, Anderton's Elements of Set Theory, Exercise 2. Show that no two of the three sets, empty set, set containing empty set, and set containing empty set, are equal to each other. So let's just, as always, ground ourselves in first principles. What does it mean for two sets to be equal to each other? At least in set theory, there's a very specific meaning for sets to be equal to each other. And we say that if, oh, whoops, that's not the right color, at least not right now. If A and B are sets, then A equals B if and only if A is a subset of B and B is a subset of A. Both of these must be true. And again, as you probably read in the book, or if you saw exercise 1, A is a subset of B if every element of A is also an element of B. B is a subset of A if every element of B is also an element of A. So what does it mean for two sets to be equal? Under these definitions, A and B are equal if and only if they contain the same elements. Okay, but that can get a little bit more vague, so I'm going to use this definition to solve this problem. Okay, so if A and B are equal, if and only if A is a subset of B and B is a subset of A, then for two sets to be unequal, all we have to show is that either A is not a subset of B or B is not a subset of A. So I'm going to write this out. I'm going to write it out in, let's say, blue. A does not equal B if A is not a subset of B, or I'm going to capitalize stuff. I feel like it's more dramatic, more fun. And if A is not a subset of B, or B is not a subset of A. So we want to show that no two of the three sets are equal to each other, which gives us three sub-goals. So this does not equal this set. This is so hard. Why? Okay. The second sub-goal is to show that the empty set is not equal to the set containing the empty set. Finally, that this is not equal to this. Okay, so these are our goals. I'm actually going to color all these in dark blue because those are our pseudo problem statements. Okay, so what do we need to show? We need to show that either this is not a subset of this, or this is not a subset of that. Okay, so how do we go about this? Now, the easiest thing is to think of the quote-unquote bigger set. Of course, the empty set contains no element, but the set containing the empty set contains one element, that being the empty set. So we can show that this is not a subset of this because, as we said before, in any well-founded set of axioms for set theory, a set does not contain itself. If you want a better reasoning for that, ask Anderton. But anywho, this can't hold. Like this is not true. Never. That's this bad. You break math. It's akin to dividing by zero. You shouldn't do it. So since there exists an element on this set that is not contained in this, then we arrived at our desired conclusion. We have that one of the two sets is not a subset of the other. Hence, this is not equal to this. Okay. I sometimes give explanations that are a little too long-winded. I hope that does not detract from the learning experience for you. And now I can do the exact same thing for the second one, right? So let's do this. Let's ask, is this a subset of this? Well, we want to ask also an equivalent question, since this set only has one element, is this set inside the empty set? Well, the empty set itself is defined to contain no elements. It is empty. So of course not. It's not true. So I'm so frustrated. I can't wait to get to abstract sets because I can stop drawing braces and my suffering can finally end. Okay, so I'm going to separate these line by line. So our question is the left-hand side a subset of the right-hand side? Well, left-hand side cannot be possibly within the empty set because the empty set has nothing in it. So the left-hand side is not a subset of the right-hand side. So left-hand side and the right-hand side cannot be equal by our definition of equality. Finally, we can do it either way, but let's do it in the easier way first. And you ask the question, the perennial question. Is this true? Or I keep being inconsistent before I put the question marks, but this is equivalent, and this is just a symbol, a logical symbol for if and only if, which can be interpreted as equivalence, just in case you hadn't seen it before. This is equivalent to asking whether this set is inside this set. And again, no, not good. If you ever try to do this, stop, because you're using a not well-founded set theory, and that's bad. Because old mathematicians who are now dead said so. Also because you get paradoxes, but anywho. Cool, so this is not here. So it's not true that this is a subset of this. Oh, handwriting just keeps getting sloppier and sloppier. Okay. And therefore, not equal this. Okay, cool. So we showed this one is true. We showed this one is true. And we showed this one is true. So we just showed that no two of the sets, empty set, comma, set containing, empty set, comma, and set containing, empty set are equal to each other. And we're done.